Based on what we've been discussing about the sampling distribution, sampling variabilities, and the characteristics of samples, this is so far what we know. If we know the population mean mu, in the previous example it was 50, the population standard deviation sigma, it was the 20, and the number of observations in the sample, it was a number of values in the sample, which was 100, because it was a sample of 100. And you can also determine the shape, center, and the spread of the sample distribution for the sample mean. Okay, the shape of the sampling distribution for M. The sampling distribution of M, it will be normal distribution if one or both are correct. Okay, if one, the population from which the samples are selected is a normal distribution, or the number of observations in the sample is more than 30. In the previous example, we took the sample of 100, so the distribution is going to be normal. Remember, we said the values from the samples are similar to the value in the parameters, population parameter. You know, it's the reason why it's true is that, you know, suppose we just take, you know, a sample of 5, you know, values from the population. That's not always true, you know, but because we're taking so many numbers of, you know, data from the population, the value in a sample kind of, you know, resembles the value in a population. So there's some, you know, absolute number or a threshold, you know, beyond which the sample start to you know, forming us the shape that's similar to the population. This magic number is 30. So, you know, in this case we're taking a sample 100, you know, it's way over the magic number 30. So that's why, you know, the shape or the characteristics of the sample is resembling the characteristics of the population. See, this just talking about the, you know, a mean for in this example, but, you know, mean for this sample, mean from this sample, mean of this sample, this, that, you know, they're all similar, resembles the population mean. The reason is we took 100, sample of 100, you know, which is over the threshold of 30. You know, that's why you know, they resemble the population mean. It is possible that if we only take 5, it may not resemble. But even if it's only a sample of 5, it actually resembles the population mean if the population has a normal shape. That's what it says. That's what it means. So shape can be a normal, you know, in this. The center of the sampling distribution for M, the sampling distribution in M will have a mean that is going to be the expected value equal to the mean of the population from which the samples are drawn. So population mean was 50. So expected value, in other words, the sampling distribution for M. So the mean of sampling distribution, you know, mean of samples, all the samples, that's going to be the same. So expected value is going to be 50 in the previous example. the spread. In other words, it's the standard deviation, the spread of the sampling distribution for M. In other words, the sampling distribution of means will have a standard deviation that can be calculated as follows, So it's a standard deviation of the population divided by the square root of the sampling population. So in our example, the standard error is going to be, okay, this is 20, right? And we had a sample of 100, so this is going to be a 100 squared, which is, square root of 100, so it's going to be 10. So it's going to be 2. So standard error is going to be 2 in this example. So this is kind of important. We have to be able to say this and write this in this format. Okay, that's if the population distribution is a normal distribution, or if an n is greater than 30, we can describe the sampling distribution for M as the sampling distribution M is normally distributed with a mean of mu and a standard deviation of this, sigma divided by square root n. So let's use actual numbers from the example. So in a previous example, in our example, you say the sampling distribution of M is normally distributed with an expected value of 50 and a standard error of 2. Okay, suppose you take a random sample size of 25 from a population with a mean of 50 and a standard deviation of 20. So it's the same population, but in this time we're taking a sample of 25 instead of a sample of 100. Let's calculate the standard error. Well, actually, let's look at the shape, mean, and standard deviation of the sampling distribution for M. In other words, standard error. Done. Okay, the distribution is going to be normal because the shape of the sampling distribution. Because population distribution is normal, so sampling distribution for M is going to be a normal shape too. And we know that the mean of the sampling distribution for M would be equal to the population mean, so it's 50. What's going to be different is the standard error. And we know standard deviation, this is its formula, right? So it's going to be 20 divided by square root of 25 in this time. So if it's 5 divided by 20, it's going to be 4. Let's see. So it's going to be this. So what it means is that the normal distribution with a mean of 50 and a standard deviation of 4. So we say expected value of M is 50 and the standard error of the mean is 4. In other words, this was earlier it was how much? 2. Now that the standard error is going to be 4, so it's much more widespread. Why is error is doubled in this example? There are more chances of randomness in when you have a smaller sample. You can't always have the uniformity. If you have a really small sample, if you don't get this idea, you're gonna have a hard time understanding this. But so for the first sampling distribution, the typical amount of sampling error for M was about 2 points. For the second sampling distribution, the typical amount of sampling error of M was about 4 points. Why the difference? Okay, it's a different sampling size. If we have more sample numbers, data, you know, the error is going to be smaller. But if you only have limited, you know, much smaller sample, then, you know, of course it's missing a lot of data, so that error is going to be larger, you know. It's clear that standard error is a function of a sample size. Larger sample size means a smaller standard error for M. If you don't get this idea, you know, it's going to be hard for you to understand. And you know, the reason why it makes sense is that the larger samples would typically be more representative of the population than a smaller sample. That's the exact reason why in a statistic calculated on a large samples would typically be better estimates of the population parameters, because, you know, the number of the sample is getting closer to the actual number of population, so no wonder it's getting closer to and more accurate than, you know, the smaller sample. So it makes sense that the sample means calculated on a sample 100 will typically have less error than the sample means calculated on a sample of 25. You know, suppose the population is 150, then calculating the value out of 100 is going to be definitely closer to the actual population than calculating out of 25, you know. So let's have some practice, huh?